Hi, I'm Ane, and today I'll be talking about mitigating bias in subset selection when the protected attributes can be noisy. This is joint work with Professor Elisa Celis at Yale University. We study the subset selection problem where one is given m items and each item has a utility associated to it. This utility is the value it adds to the subset if it's included in it. Then we would like to select a subset of size n such that the sum of utilities of items in this subset is maximized. This problem has several applications. For example, given a search query, an image search engine selects a subset of images to show to the user. Similarly, given a description of the candidates, online recruiting portals such as LinkedIn show a subset of the candidates to a recruiter. More specifically, we'll be interested in the problem of fair subset selection, where we want to select a subset which, quote unquote, equitably represents different social groups. For example, given an occupation-based query, the image search engine might want to display a subset of images which match the distribution of genders actually found in that particular occupation. The online recruiting portal might want to show a subset of users to the recruiter which proportionally represent each race. Many of these problems also have a ranking component, where once the subset of items is selected, it also has to be ranked. However, these two tasks are often done separately from each other, where the subset is first selected and then it's ranked. In that setting, the discussion we'll have in the rest of the talk would also apply to this version of the ranking problem. Several prior works have studied the problem of fair subset selection and its generalizations. We'll specifically look at the following setting. For each item I, we have a protected attribute Zi, which can represent socially salient attributes of this item, such as its race, gender, or ethnicity. Apart from this, for each item, we also have other features AI, which contain other information about this item. Picking the subset of items with a particular protected attribute, we partition the set of items into multiple groups. We'll be interested in how many items a subset selects from each of these protected groups. We say a subset S is fair if the number of items it picks from each protected group satisfies some lower bounds and upper bounds. Importantly, we do not fix these lower bounds. That is, we do not fix the notion of fairness. Instead, we take these lower bounds and upper bounds as inputs. Several prior works have studied such constraints, and they are known to encapsulate a wide class of fairness metrics. For example, if you would like to ensure equal representation and there are three protected groups, then we can set the lower bounds to be n by 3. And this would ensure that the subset has to satisfy equal representation constraints. However, this approach inherently assumes that we know the protected attributes for each of the items. However, in practice, these attributes can be noisy for some or most of the items. For example, in the healthcare setting, several studies have shown that ethnic information can be left blank for some of the patients or most of them. This was recently highlighted in media in the context of the current pandemic. Specifically, during the initial phases of the vaccination drive in the United States, it was found that the ethnic information of more than 50% of the people who received the vaccination shots were missing. Further, if you want to consider images on the internet, then none of these images have protected attributes either. So how can we deal with this problem of missing protected attributes? Well, one option is to use algorithmic approaches to impute these protected attributes. For example, given the last name and location of an individual, we can try to predict their race. Further, or as another example, we can use a machine learning based classifier to try to predict the apparent gender of a person depicted in an image. But such approaches are bound to have errors and noise, which can even vary across the protected groups. So why is such errors an issue? Consider the following toy example where we want to ensure equal representation between the blue and green items. Here, the colors of the items are noisy, and so we are not sure of how many items we select from each group. Suppose to satisfy the equal representation constraint, an algorithm selects the following set of items. It is possible that out of these items, the ones who are outlined in red have an incorrect protected attribute. In this case, the resulting subset definitely doesn't satisfy the equal representation constraint, but it might also end up being more unbiased or discriminatory than the initial subset we started with. Then the main question we ask in this work is fair subset selection even possible when the protected attributes are noisy? To address this question, we consider a model of noise. Here, for each item, we now also have a noisy protected attribute, hat zi. This noisy attribute may not be equal to the true protected attribute. Also note that now we do not actually know the true protected attribute and only observe its noisy version. Then, in this noise model, for each item I, we assume that we have the probabilities that we know the probability that its true protected attribute would take a particular value conditioned on the other information we have about this item. Now, prior subset selection approaches do not take such probabilities into account. And so one approach to make prior approaches work is for each item uh, to set the protected attributes of each item to its most likely value. However, as we saw in the previous slide, if the error rates vary across groups, then this approach can even aggravate the underlying bias. So the question remains, how can we design noise-aware approaches which take the above probabilities into account for fair subset selection? Before presenting our approach, we recall the original target problem. Here, we want to maximize the sum of utilities of the items in the subset subject to some fairness constraints. Specifically, we place fairness constraints on the number of items the subset selects from each protected group. Then we propose the following denoise problem, which is identical to the target problem, except that the fairness constraints are placed on the expected number of items the subset selects from each protected group. Then, as a preliminary result, we show that any solution of the denoise problem violates the fairness constraint of the target problem by a small amount with high probability. Thus, one might hope that finding a solution of the denoise program would also give us a reasonable solution of the target program. However, the issue is that the denoise program turns out to be NP hard. And so the question now becomes, is there an efficient approximation algorithm for the denoise problem? Our main theoretical result is exactly this. We show that yes, there is an efficient algorithm for the denoise problem. And this in turn also implies an efficient approximation algorithm for the target program. More specifically, our theorem is that there is an efficient algorithm which, given the probabilistic noise information, outputs a subset which has the optimal value for the target problem and violates its fairness constraints by at most a small multiplicative amount with high probability. Note that the approximation here is not in the objective, but in the constraints. The actual algorithm turns out to be pretty simple. It solves the linear programming relaxation of the denoise program and then rounds the resulting solution. In our empirical study, we consider multiple simulations, but in this talk, I'll be focusing on one. I invite you to read the rest of the paper for other simulations. In the simulation, we compare our approach to prior approaches for subset selection, which do not take noise information into account. This particular simulation considers an image dataset, which is from a recent paper by Celis and Keswani. This dataset contains the top 100 Google image search results for 96 occupation-based queries. The motivating example application for this simulation is the following. Given a query corresponding to an occupation, an image search engine would like to display images which match the distribution of genders actually found in this particular occupation. Yeah. Now, in practice, the images which occur online do not have protected attributes, and we must use some method to derive this probabilistic information about them. To mimic this scenario, we use a CNN-based gender classifier, which predicts the apparent gender of the person depicted in the image. And we then use these probabilistic information to run our algorithm. To run prior algorithms, we first assign each image the most likely gender using this probabilistic information, and use the resulting protected attributes to run the prior subset selection algorithms. Note that importantly, this particular data set actually had crowdsourced gender labels, which allow us to measure the performance of our algorithms under the ground truth protected labels. In this simulation, we consider risk difference as the fairness metric, and we measure the utility by utility ratio, which is the ratio of the utility obtained by the algorithm compared to the optimal subset of size n, which doesn't need to satisfy any fairness constraints. Note that since we compare against the subset which doesn't satisfy fairness constraints, we don't expect this utility ratio to be bigger than 1. Then we vary the fairness constraints of all the algorithms to capture the trade-off between the utility and fairness. Specifically here, we plot this difference on the x-axis and the utility ratio the y-axis. And in this plot, our method is represented by the line in blue. We can observe that compared to prior approaches, our approach achieves a higher level of fairness with respect to risk difference, since it reaches a value more towards the far right, which denotes a higher fairness, and it has a better trade-off between utility and the fairness metric. In the paper, we also consider other standard fairness metrics such as selection lift, but I omit the plots for those here. Then the key takeaways from our work are the following. We note that accounting for noise in fair algorithms is important, and not doing so can have adverse effects. We develop an efficient algorithm for fair subset selection, which, given probabilistic information, can satisfy one from a large class of fairness constraints with a small multiplicative error with high probability. Empirically, we observe that this algorithm has a higher level of fairness and a better utility versus fairness trade-off compared to prior approaches which do not take noise into account. Our work leaves several future directions open. First, we consider a, a specific noise model, and it could be important to consider extensions to other models depending on what information is available in practice. Next, we consider the subset selection problem, but one could generalize this to the ranking problem or consider the online subset selection problem. Finally, it is important to study uh, our approach as part of a broader system for mitigating bias in mitigating bias with noisy protected attributes.